Hello everyone, the live stream will be up in about 5 minutes, maybe 3. Okay, bye. How are you? Wait this around a bit.
No, this is the week. Yeah, I left. I just left some stuff. No, it's a new one. It's not super like the way that the man moves, really it kind of wants the inertia it's what you'd like to use something. Otherwise, it makes sense. I really go to something that's it's cool. Like if you're in a position to do it on a partner, we don't have to get around.
You guys think you travel together?
Yeah, we both run. It's not common, but we use I'll be based the beauty of like flying because I fly on the road. Both is on the road. That's not what we're doing.
Because Jordan in Germany and she was
No, she was in Germany as well, but for a couple of months there we were working in different clients. So she was traveling to a different city. And I was literally working from home.
I was going to say yes.
So, hello everyone on the live stream. We're just about to start. So, hello everyone and welcome to the Ethereum Engineering Group meetup. So today we're going to talk about consensus algorithms. So we're going to talk about proof of work, proof of stake and proof of authority based algorithms. And I'm going to talk. Rob Dawson back there, who's busy behind a laptop, is going to talk, and so is Adrian over there. So let's lead off. So consensus algorithms, it's all about, you've got a decentralized network of nodes. How do you come to an agreement on what transaction should be put into the next block? You know, how do you come to an agreement on what truth is all about? And so I'm going to walk you through some algorithms. It's focused on the Ethereum ecosystem. There are other algorithms that are used by other blockchain systems, but we're just going to focus on Ethereum today. So, as I said, I'm going to talk about Ethereum PoW. We're going to have PoS and Casper talked about by Rob, and IBFT and others talked about by Adrian. So, proof of work. The overall process, the meta process that you're looking at is the miner assembles a set of transactions that are going to go into the block, and also some uncles. And then we create a candidate block, you do the mining algorithm, and then once you've the first miner solved the puzzle problem, it publishes its proof, and then everyone can verify it, and then it's agreed on as the block. So that's a very high level process. So let's drill into that a little bit. So we've got the miners, and so they assemble the set of transactions. And how do they do that? You know, if you've got lots and lots of transactions, more transactions than are going to fit into a block, how do you prioritise them? Well, you prioritise them based on who's going to pay the most. So everyone who wants to execute some code has to pay a gas price. And the idea is that you look at the amount of gas that they're prepared to pay, the amount of money that they're prepared to pay for their transaction, and if someone's going to pay you this much money, someone else is going to pay this much money, who are you going to prioritise to mine first? So the obvious ramification for people who are submitting transactions is if you want your transaction to be definitely mined in the next block, you pay a lot of gas. And if you just want to pay a little bit, but you don't care if it gets mined sometime in the next few seconds, the next few minutes, or even the next hour, you pay almost nothing. You know, you pay maybe 100 times or 1,000 times less. So some miners will accept your transaction even if you're paying 1,000 times less than the maximum that you might pay. But it might take a while for your transaction to end up in a time period when not many transactions are available that want to be mined. So what's an uncle, I hear you ask? So you've got a huge distributed network of about 30,000 nodes in Ethereum. And you can imagine that at one end of the network, you could be assembling a set of transactions which you put into a block, and then you could end up, say, creating this block 101, which builds off block 100, and then you're creating block 102. But meanwhile, at the other end of the network, someone could have mined block 101A. And because in Bitcoin, you've got quite large inter-block times, so large block periods, whereas in Ethereum, it's down to about 12 or 15 seconds. It started off at 12 seconds, and then the decision was made to increase it to 15. And so the reason that you're doing that is because you're worried about the amount of time it takes for blocks to actually get pushed across the network. And so what you do is you allow for the fact that, well, this might have some transactions that this doesn't have in it, so let's integrate the work that's been done so that then, because if you didn't include this block, then all those transactions that are in there would have to be pushed back into the transaction pool, bringing in more transactions. So then the miners create a candidate block, which they're going to so they're going to create a candidate block header. So what they do is they put all of this information together. So parent hash being the message digest of the previous block. And then the OMAs. So OMAs apparently is a gentle neutral term for uncle. There you go. We've all learned a new thing today, haven't we? Beneficiary. So in Bitcoin, you have a coin-based transaction which pays the actual miner. So you don't need to do that because we don't have an unspent transaction output style of payment. In Ethereum, you actually just have addresses, and so that's the beneficiary's address, so the miner's address. And then your state root, so the root of the Patricia Merkle tree, after all the state's been updated, given the transactions, the transaction root, receipts, and so a whole heap of other stuff. But in particular, you've got this mix hashing nodes down the bottom. They're not included in that hash that you do of the candidate block header. And in fact, this diagram here, you should go to that link there and you can have a look at this diagram. And it's actually a massive diagram that someone did about 2 years ago. And I'm really kicking myself that 2 years ago I didn't come across this diagram because it's really good. Anyway, so someone, if they ever meet this person, should buy them a beer or something like that. So anyway, you put together all the information of what your block is going to look like, assuming that you're the one who mines it. And then all the miners have to solve a puzzle problem. So we'll remember from our cryptography part 1, actually part 2, maybe I talked about this in the cryptography sessions about puzzle problems, but they're essentially time memory hard problems where you can prove you've done some sort of computational work to someone. So maybe you've had to hash something 1,000 times, something like that. You can prove that you've done computation. And so that's what a puzzle problem is. And so the idea is come up with a way of proving that these people, these miners, have done that computation. So we've got a block period happens every 15 seconds. And then in the proof of work algorithm, you've got this concept of epoch. which is every 30,000 blocks. And so if you do the maths, you work out that's about 125 hours, which is every, 4 or 5 days. So the idea is each epoch, the parameters for creating blocks increases, so it becomes harder. So it's trying to take into account that you might have more memory in the CPUs, or maybe the CPUs become more powerful. So each epoch, what you do is you work out a seed value. And so that seed value is just the message digest of the previous seed value from the last epoch. So it just starts off at 0, and then each 4 days or so, you create a new seed value just based on the last one. So something that you could pre-calculate now for all of the seed values off to infinity. You generate a cache based on the seed value. So this is another deterministic algorithm, and you generate a memory array, which is initially it was 16 bytes. Based on the cache, you generate a data set. So the idea is that those 256 bytes are available to you, but you could quickly generate each entry in the table if you just needed to generate 1 or 2 entries, or some small number of entries. So the full nodes, or the mining nodes, they have to keep, or they keep this full data set in memory. Whereas if you're, say, a telephone or some sort of light client, you would generate this on the fly, or the pieces of it that you need. And so it's actually a really smart algorithm. You've got a small enough, this cache, which is small enough that even a limited device like my telephone over there could easily have in memory, and it could be pretty fast. And then you can quickly generate the other bits that you need when you need them. Or if you want to be a mining node and do things really quickly, then you have it all in memory, but then you're a grunty server style, in some sort of data center style computer. So, as I was saying, as time goes on, the parameters increase to make things harder. And so the cache started off at 16 megabytes back in 2014-ish, and then it's grown by another 128 kilobytes each epoch. The actual total data set started off at a gig and has increased by about 8 megabytes each epoch. So currently we're at block number lat, which is epoch number 195. And so the cache, right at the moment, it's about 40 meg, and the data set's about 2.5 gig, based on my calculation. So I'm pretty sure they're right. So, that's a fair bit of RAM, but not a lot of RAM. So, each epoch is 125 hours long, and so all of the nodes across the network simultaneously realise that they're now moving to the next epoch, so they all switch and use a new cache and a new data set each time we hit a new epoch. So obviously, if you're a full node, or if you're a miner, you're going to have pre-calculated that, because the last thing you're going to want to do is spend a minute or two generating this and stop mining for a bit. So you're going to have some computer that's going to pre-calculate all of these data sets for all epochs, and we'll be ready to just slot them in as the epoch comes. So once you've got this huge data set, then what you do is use an algorithm called a hashimoto-like algorithm. So Hashimoto is a particular algorithm, and then of course it's changed and changed and changed. So now it's called a Hashimoto-like algorithm, so it's similar. And essentially it does lots of hashing, and essentially it does grab 64 blocks out of that data set. So each data set item took 256 blocks from the cache to create a data set item, and now you're doing 64 of them. So that means you're doing 64 times 256 accesses out of the cache if you're generating it on the fly. So the output of all of this is a mix hash, which is an intermediate result, and the result itself, which is the message digest of the block header. So you remember how we had our candidate block header that we were thinking about having? A nonce value, so a number once, so that's your own unique value, and then the mix hash, which was this intermediate value. So you're mixing everything together, you've got an intermediate value, you're combining it with the starting parameters that your node has got, and then you're producing a result. And then when you want to work out whether you've mined the right block, you say, is my result that I've just come up with as an integer, is it less than the target? And so the target is a value that is calculated from block to block, and the goal is to make sure that the interblock period is 15 seconds. So you've got the heuristic of how are we going, you know, how's the actual hashing power of the network going? Should we make this target bigger or smaller to make the actual, you know, probability of finding the correct hash or a hash that gives a result that's less than the target? You know, what's the probability? Can we hit bang on 15 seconds? So obviously it's a variable thing because you've got it's a probabilistic thing that you're actually going to come up with a value. And yeah, so what you do is you publish the value using the F protocol. So I think Rob Dawson did a talk on peer-to-peer protocols about a month or two ago, and in that one of those protocols was the F protocol, and that's how you push out, here is my new block that I've mined. So all of these nodes, they can look at the values that are coming in, the person saying, hey, here's a new block. And rather than them, because you could do a denial of service attack where you get them to get all the nodes to do a fair bit of work to calculate whether that really is a valid block or not, because you're not just going to accept it just because some node said this is a valid block. You're going to have to calculate it. So as a starting point, you do this calculation based on the intermediate value. The reason why you do that is the probability of finding a value that will be the probability of coming up with this means that you've got to have a pre-image. But then maybe you could come up with headers that isn't a valid header as spam. But anyway, then it does some level of protection before doing the full Hashimoto algorithm. So I was going to do a lovely graph about finality, a probabilistic finality, but I ran out of time. And so if we ever do this presentation again, or have a specific presentation on proof of work, I promise this slide will have a lovely graph in it, and I'll be able to explain the probability. So in summary, proof of work gives you leaderless block creation. So there is no leader. Each of those nodes is independently doing that proof of work calculation. It gives you architectural decentralization. So there isn't, if one of those miners blows up, loses power or whatever, it doesn't stop the other miners from coming up with valid blocks. Is there political decentralization? Now, I think my next slide is, yep. So in my next slide here, I've got the overall hashing power and who has actually mined the best block for each time period. And this is actually quite interesting. So you know how we talk about these 51% attacks? So if we have a little look here, you can see that we've got 1, 2, 3, or even probably it's almost 1, 2, 3, 4. And then, you know, so these are, if these are owned by completely different organisations, so that's good. But if those 3 collaborated, or if those 4 collaborated, then you could imagine you could have a problem. They could coordinate their activities to come up with, you know, what block they want to produce. So though we have architectural decentralization, the political decentralization is a bit, you know, have to have a think about it. So when we now look at some of these other algorithms, they're maybe not as bad, you know, from the political centralization as you might think. There are some things that you might want to have a look at to learn more. And proof of stake. Oops, there you go. Sorry.
So thank you, Peter, and you've done an excellent job of doing great detail with proof of work. The proof of stake is going to be like much higher level. I'm going to keep it high level because the actual details of proof of stake in Ethereum is still in active development. And so there's been talk for a long time, you'll hear the words Casper being talked about. And so Casper has been 3 to 6 months away since I started at Consensus, which was in October last year. It's still 3 to 6 months away, and it's probably more on that 6-month end than the 3-month end. So I'm going to talk about why you care about proof of stake, what it is, and sort of how it works a little bit, and a little bit about when it might be coming. So three sort of good questions for us to try and answer, and hopefully we'll come back with some answers for that. So why? The first is the cost of proof of work. And this is kind of foundational to all the other reasons as well. And so if you look at the cost of proof of work, it's kind of the amount of energy that goes into proof of work, probably across, like, you spread from just Ethereum and you include Bitcoin. If you just pick Bitcoin or just pick Ethereum, it's like the cost of running, the amount of power that you use for proof of work is the same that countries use for all of their energy use. So I think Iceland's sort of size is definitely less than what's being used by proof of work these days. So you can look on the net, there's a bunch of different charts which show over time, and you can sort of see the amount of energy that's being used by Bitcoin, for example, kind of has that, you know, that growth curve that you love if it's your product and its uptake, but you don't love if it's the impact on the environment because you're doing some sort of an inefficient thing. The next thing with the proof of stake is, like Peter's slide, where you've got these sort of mining pools in Ethereum, where you've got essentially, you could pick this Ethermine plus any two of the other big ones, and you've got like a break of the 51% consensus. You've got that same sort of thing. So proof of stake is something to try and address that, and that's, you know, a common picture across many of the blockchains. So definitely Bitcoin has similar sorts of you know, effective centralization points. So our decentralized technology, which is magic, has ended up with a little bit of centralization happening again. So proof of stake is sort of aiming to address that. And I guess with that, proof of stake was something that Vitalik sort of had, yet that was always a goal with Ethereum, was to move to proof of stake. And so the thing that you kind of need though for proof of stake is enough people that are going to be doing the work for it to be a viable option first. And so that's why it's, you know, been on the roadmap and something to happen. And the other thing that you need is a migration path that everyone can agree to, and a good sort of solid protocol for working with it. And those migration path and the good solid protocol are the bits that are taking the time for us to get there. So I guess that green, so, you know, we're going to save the planet by not destroying the planet with blockchain. And the other thing that is there with proof of stake is putting in some strong economic incentives for people to do the right thing. And so there's the idea of slashing a stake if you cheat. And so I will talk about that shortly. How does it work? From the high level, how does it work? Well, what you do is you put aside a bit of money or ether, some sort of cryptocurrency, and you say, this is my stake that I'm putting into, so depositing the money, the ether, into, say, a smart contract. That's your stake. Everyone can see that you've deposited this large amount of money. And so that idea is that the validators have locked up some of their coins as stake. After that, those people start validating their blocks. And when they're validating a block, they put a bet on what they think the right block is going to be. The people that make the right bet win money and income from doing that. So does that kind of at a high level make sense? Stunned faces, some nods, some shaking heads. Okay, so proof of work.
Can I ask a question?
Please do.
Okay, you say that they'll start validating the block. What is validating the block?
So
What is the process?
Yeah,
That's
kind
the
of.
difficulty with proof of work, we understand the mathematical problem.
Yep.
Right? The caching the nodes and creating something that's less than
Yep.
unknown value. What is validating? You can read what Brad Zampa has written, you can read a whole heap of stuff, but they never actually explain what validating. What is the process? What's the mechanism of validating?
Yep. So it's similar to, I guess, the proof of work. You're taking together a whole bunch of transactions and inserting them and saying, here's my block. And then you do the crypto proof, which says, yep, this is definitely to show that you've done that work, to validate that block. With here, it's essentially just taking these things, putting them together and saying, this is the block that I propose. And so you're not doing the proof of work on it, you're just saying, here is the block that I propose.
So it's a subjective decision.
Yep. Yep.
Okay.
as per normal, I guess proof of work in some ways is a subjective decision as well, because you're picking which transactions you're inserting into the block.
Yeah, but you're making sure they're valid. I mean, validating from the perspective of, is this a valid transaction? Are you, like spending money you don't have? Are you, when you executed that solidity code, did it throw an exception, and hence it shouldn't have been included in the block anyway, because maybe there was some precondition that was set up in the previous transaction. So that is part of the validation.
Yep.
That's the validation process.
So with the bet, who decides who wins the bet? How does that work?
That's a good question.
That was my next question.
Yeah, this is part of the problem. How do you work out, how do you randomly assign who wins in a deterministic system?
And is it like the Price is Right, where the person closest to the number wins, or like?
Well, no, this is an open question. There's a conference down on the Gold Coast where I'm presenting on how do you, in a decentralized way, come up with a random number. So, but that's research.
So I think a part of it's going to be a smart contract, and some of it might end up being a round robin type system where you've got a list of known validators that are working on it. And so Adrian's going to talk about the way that IBFT works, and some of those, some of the BFT, so the Byzantine fault tolerant sort of algorithms and ideas that are coming from there, are influencing some of the, I guess.
So you already have to be a known validator. You can't just be.
Yeah, for this you definitely are a known validator. So you're as
So
a
it's
party.
not like proof of work where you can just connect and try to win the block, and if you win, that's great.
That's right. Yep. Yep. So you need to be a known validator that has.
So who knows? Is there a centralized database of all of the validators?
There's a smart contract that sits on the blockchain. Is typically the way that people have talked about it being. So
when you say you've got to be a known validator, doesn't it just really mean you've got to be know your customer, anti-money laundering, or anything like that? That's not
most likely the way that you're known is not really known, but you are in advance declaring yourself to be a validator by.
So the proof is it's the stake that you put is the proof that
That's
you're
right.
a known validator.
Yep.
But you don't have to supply any kind of information about what kind of rig you're running or.
The regulator gets involved.
Yep. So I think a part of that then is with the gaming and the betting of it. So a part of it is going to be making sure that people don't bet on divergent chains and double bet. So if you can bet twice, then you effectively are not staking anything. And so a part of the way that the work is going to have to be is if you do end up betting, having the idea of burning the money that you did bet. And so on this block being the right answer, so that I can get it both ways and always win. If that's detected by doing this double bet, you're actually risking losing money. So there's a strong, I guess, financial disincentives for doing the wrong thing. Okay, so I have kept it very, very high. I have not covered any details. There are lots and lots of questions, and lots of very good questions, most of which are actually going to be covered in how the implementation is done and what the implementation details are. Because it hasn't actually been implemented, it's hard to say what the exact answers are going to be. And so one of the things that's happening in Ethereum at the moment is they've always talked about Casper being one of the next milestones that was going to be like a hard fork, which is going to be the Casper hard fork. That's now changed, I think mainly influenced by CryptoKitties, that being able to have some sort of scaling solution is where a lot of the research emphasis has been. And so the idea of whatever the proof of stake implementation is going to be, it's now coupled tightly with the sharding work that's happening. And so there's, I think, a link there, so that notes.ethereum.org with a really friendly URL, and sitting there has the details of what the current direction is going to be. And the thing that I guess has been the gold standard for how Casper was going to be rolled out has been the ETH 11101, and so that is now almost certainly not how it's going to be implemented. Mainly because the whole sharding work that's being driven is I guess pushing it in a slightly different direction. So the ideas that we've been talking about, or have been talked about for a long time, about how Casper and proof of stake is going to work in Ethereum, and here's the direction we're going in, it's not quite going to be the direction that it goes in.
Actually, the problem with Flag Xantha is left with Ethereum is no working Arch.
Sure. I guess so while some people have left and there's been some movement around, I think there's a bunch of really smart people that are looking at the mix. So yeah, I mean, I think there's Consensus Hub people. There's the Ethereum Foundation. Vitalik is not a dull guy, and he's sort of working on it as well.
And for those people who are busy writing down that URL, don't forget the slides have been put onto the Slack workspace in general.
Okay, so going back to my how much to stake slide. So the answer is it depends on the actual implementation. So the original Casper, there's a configure. So Casper, the original version of Casper was sort of sitting as a smart contract where you would stake make your stake against that smart contract. It's talking about 1,000 to 1,500 sort of ETH, which in today's dollars it is like 600,000 to about $1 million worth of staking for it. The thing with that though is that there's startups that are saying, okay, join our pool and be a part of our stake, and so you don't need to stake the whole 1,000 ETH for yourself. You can join a staking pool and they will run something on a cloud host which does all the mining work and does the staking for you, and you get to be a part of it. Yep.
What's to stop those pools just turning into the same kind of large slice of the pie that you see with proof of work today?
I guess it's that financial stake, and there is that risk, I guess, still. Not sure.
Is there a capping on the number of validators? Because I know that like EOS has capped its validation to 21, which is highly criticised substantially. Is there any ether going to be a capping on the number of validators, or they haven't decided?
I guess a cap of the max amount of ether that you could put in, as in
number of validators, the actual number of validators.
Yeah, so I don't think there's a hard cap, apart from the fact that there's a cap on the